Well, welcome to chapter 9. I have my power aid ready. Can we see the power aid? Yes, we can see the power aid there. And as I mentioned, this is going to be a long lecture, so you might take it in some stages, and I may actually pause it a time or two because my voice may just give out. It is amazing to me, and those of you who have been on Zoom may notice this, it is much more tiring to talk for 1 hour to Zoom than it is to talk for 3 or 4 or 5 hours to regular people in a live setting. And I've been feeling that quite a bit lately. So if I stop to take a drink every now and then, uh, forgive me, and now you know why. But this is usually a lecture area that is divided into 2 or really even 2.5 chapters in previous semesters, and it's now collapsed all into one. And there are all sorts of things that I'd like to say, and I'm going to try not to go too long and too long-winded on different things, but I hope it will be helpful for you, and I hope it'll be something that you will enjoy, because we're looking at our nearest neighbor planets. Yay, we have Venus and we have Mars. Actually, we have Mars over there. No, it's this. I'm sort of seeing that's Mars over there, and this is Venus over here, and Earth is right behind me. That one's easy to get there. Yeah, Mars is smaller than us. Okay, Mars is smaller than us. Venus is about the same size as we are. So when we look at them in geological terms, we're talking about some surface issues, in which case Mars is going to be, my hand disappears there. Oh, and now we have a lamp. Hey, Mars is going to be more the twin of the Earth. And if we're talking about being below the surface, Venus over here is more the twin of the Earth. Plus, it's about the same size. So without any further ado, let me get on to our sharing of the screen. And here we are with Cosmic Perspective. Once again, we're up to the right edition. One of the things you might be hearing in the background, I don't know if you can hear it or not, but we seem to be developing some thunder in the background. I don't know whether it's going to start raining or not, but if you hear something weird in the background, that is probably what's happening. We're going to look at planetary geology, which is Earth and the other terrestrial planets. Remember, the terrestrial planets are Mercury, Venus, Earth, and Mars, and we're going to throw the moon in there for good measure. We could apply some of these principles also to the moons of Jupiter, Io, Europa, Ganymede, and Callisto. We could apply some of this to Titan around Saturn or Triton around Neptune. We're not really going to, because they're a little bit further out, but some of the things, when we get to those, as we are looking at those in more detail, I might reference back to this chapter. In particular, these volcanoes that you see here could easily be happening on Io, which is one of the moons of Jupiter. So again, here we are. If we sort of look at the different planets, we can sort of see right away they look different from each other. The two that look closest to each other would be the moon and Mercury. And I've mentioned that before. If you see a picture of Mercury and think you're looking at the moon, you can be forgiven. And we'll see why as we go forward. Earth and Venus are about the same size in terms of mass and volume. Mars is about halfway, it looks like, between the moon and Earth in terms of size. And thus it is a much smaller body in terms of its internal structure and in terms of its gravity. So we'll see how these different things pan out along the way. One of the things to also note, Venus and Earth have thick atmospheres. Mars has a thin atmosphere. The moon and Mercury essentially have no atmosphere at all. That will make a difference on what happens on the surface. But right now we're going to look inside. If we slice open the Earth, we'll see that we have a core, which tends to be the highest density stuff. The heaviest stuff sinks to the center. Lots of nickel, lots of iron, lots of heavy metals down there. And we often differentiate that into an inner core and an outer core. The inner core is solidifying more. The outer core is still very molten and not solid. So it swishes around inside there. Above that, we have the mantle, which is less dense. It's got a lot of oxygen in it. We tend to think of oxygen as being stuff that we breathe, but oxygen binds to other elements along the way. So just like rust is oxidation, that's oxygen that's being leached into the metallic elements and molecules that are part of whatever is rusting. So there's a lot of oxygen in there. It's not breathable oxygen. It's part of other things. And then we live on the crust, which is the lowest density stuff, rocky stuff, granite, basalt, other kinds of stuff like that. We can tell what's going on inside. We can't actually drill down thousands of miles, despite Brendan Fraser and Journey to the Center of the Earth. We don't do that. But we can look inside with various waves, especially when we have an impact somewhere and it rattles the planet, or we have earthquakes, and we have earthquakes by the thousands every single day. So the earthquakes will put out waves, some of which will be blocked by our core, some of which will be bent and maneuvered by the core, and some of which will miss the core entirely. And so we can judge what's where inside and the density levels that are happening inside there. Two types of waves. One is called a P wave, which is a pressure wave. And that's the kind of thing that just sort of shakes you back and forth. And then we have the S waves, which are sinusoidal waves. So just say S wave for short. If you've ever seen a video of a ridge in an earthquake that's sort of doing this kind of thing, that's the sinusoidal waves. Those are the really destructive ones. Those are also the ones that get blocked quickest. Pressure waves, however, will go through a lot, but you can usually figure out how to reinforce against something that's sort of going like this rather than twisting and torquing kinds of forces. So whenever you see a really destructive earthquake, it's usually the sinusoidal waves that are at issue there. But as we're looking at the P waves and S waves going through the Earth's core, there was some thunder. We see that the core is in fact able to be differentiated into a liquid and a solid portion. We have a liquid outer layer of that. And of course, that's going to be nickel and iron and other kinds of things. So it's going to be really, really hot. Brendan Fraser doesn't want to go down there. All of the planets and the moon, and when we're talking terrestrial planets, have cores that are similar. They'll have sort of nickel and iron and other heavy metals. Notice again, if we slice open Earth and Venus, they look pretty similar. When we slice open Mars, it looks similar, but it's all scaled down. When we slice open Mercury, it's just basically a big metal ball with a little bit of coating on it. And the moon has very, very little core. And if you saw the video last time on chapter 8, we talked about that theory that the Theia impact bounced twice on the Earth, shattered most of the Theia core. There wasn't much left for the moon. So the moon is a lot of crusty and mantle stuff. Mercury is a lot of core. So if we're looking beyond the surface for those, they're very different. If we're looking beyond the surface for Earth and Venus, they're very similar. Notice this dotted line thing that we have here. That is called the lithosphere, and we'll talk about that here in just a moment. But notice, I want you to notice how Earth and Venus are about the same. Mars is deeper, and the lithosphere on Mercury and the moon go all the way down to the core there. As I mentioned before, the heavier stuff is in the center. When these things are forming, all the planets in our formation kind of processes with the accretion disks, nothing is solid. Everything is sort of glomming together, and the heavier stuff is pulling towards the center. The center of gravity of Earth is actually the center of the Earth, and just maybe a little bit off-centered, but only by a couple of feet. We're not talking thousands of miles here. And when we're looking at that, that's where the gravity pulls most. So it's going to pull the heavier stuff down closer to the center. And you're going to have lighter stuff that buoys up along the way, especially if it's not all completely solid. The part that is exposed to space is the part that floats on the warmer stuff, and we call that the lithosphere. It's on our planet, it's part of the mantle and the entire crust. When we look at Venus, it's about the same. When we look at Mars, and it's gone much, much deeper into the mantle. It would be about here if this were Mars. And on the moon and Mercury, it goes all the way down to the core. Those are coolings that has cooled off. And as we cool off, the lithosphere gets more and more solid, and we lose the molten and liquid stuff that's in the center along the way. So we have a lot of insulation, as does Venus, because we're larger. The smaller you are, the faster you cool off. Now, lots of things will stretch, lots of things will pull, lots of things will tug. We don't tend to think of rock as something that stretches, but in fact, rock will stretch if it is pulled very slowly. If you pull it too rapidly, it's going to break. But if you apply a pressure to it for hundreds, maybe thousands, maybe even millions of years, it will begin to bend and flow as well in response to that along the way. Lots of things will respond over time to slow but persistent forces. And that happens in our planet and the other rocky planets as well. So there are lots of things that happen that cause geological activity. Largely, this is the heating up and cooling down of the center. And of course, that's an unequal heating and cooling process that's happening there. And especially on Earth and Venus, things are sloshing around in there. So that's going to create various geological processes. We have the residual heat from when the planets were first formed. Remember that word accretion that we talked about before? So this is the original accretion kind of heat. The gravitational potential energy becomes kinetic energy inside. One of the things that's also important is radioactive decay. That's one of the ways in which we can actually generate energy for ourselves. The batteries on a lot of space probes that go way out beyond the inner solar system often have a nuclear battery, which is essentially a bar of something like uranium or plutonium that is decaying over time. And as it decays, it heats up, and that heat is turned into whatever power the spaceship needs. So we have that happening inside our planet, inside the other planets as well. The cooling happens when the convection, the heat, goes through the processes, goes through the materials, and at a certain point near the top, it begins to release its heat. The cooler stuff will then sink back down to the bottom. Heat rises and the cool stuff sinks back down. So we get convection bubbles in this molten and liquid stuff inside of our planet. So the hot stuff rises and the cool stuff goes back down. Now, as the heat dissipates from the top of the convection bubble, it transfers by conduction to our lithosphere. And conduction is simply, say my hand is 98.6 degrees, probably actually like 98.5 because I'm usually a little bit cooler than average. I touch the wall over here, or I touch the table over here. And the wall and the table are about 75 degrees because that's the temperature in the room. That's room temperature here. That means the heat from my hand is being conducted into the table or into the wall. If I had a thermometer and could test it, I would see the wall has heated up a little bit, and I can feel my hand has cooled off a little bit along the way. Then at the top here, the heat just radiates out. On our planet, that heat radiating out actually bounces around in the atmosphere a bit before it radiates out the rest of the way into space. That's called the greenhouse effect. Greenhouse effects are good things as long as they're not runaway greenhouse effects. Without the greenhouse effect, we would freeze solid every night and then bake in the sun during the day. It's the greenhouse effect that keeps our planet temperate. Mars is cooler because it has less of a blanket, less of an atmosphere. Venus is super, super hot, as we've mentioned before, because in fact it has too much of a blanket. It's got extra blankets on it along the way. So planetary size controls how active you are. If you have enough insulation to keep yourself from cooling off like Earth and Venus, you're going to have a lot of sloshiness going on down there. You've still got a lot of heat, a lot of liquid, a lot of molten stuff. So there's a lot of movement and activity. That's going to give you earthquakes. That's going to give you volcanoes. That's going to give you stuff happening. Mars has cooled off a lot. So while there still may be some rumblings deep in the interior, things have pretty much settled down on the surface. Volcanoes are dormant, if not extinct. Not a lot of Mars quakes, and what there are tend to be pretty minor. Same is true for Mercury and the Moon. The volcanoes have shut off. The quakes are essentially not happening from the center. There may be, again, some very gentle, some very minor quakes, but often that's from various kinds of shifting due to cooling rather than anything else. The Moon and Mercury are often considered geologically dead because they don't have anything happening there. Mars is mostly dead, if you sort of think about the Princess Bride, but it's not coming back anytime soon. The way this can be calculated is this very clunky thing here, but sort of take your hand and cover the 4 pi r squared and all of that sort of stuff on your screen. All you have to look at is 3r here, because you know the 4's cancel out, the pi's cancel out, 2 out of the 3 r's cancel out. Notice you have an area and you have a volume. It's a certain size. So let's say it's 1 cubic foot. Well, what would the area be on 1 cubic foot? Well, on 1 cubic foot of whatever, you're going to have sort of like 1 foot, 1 foot, 1 foot, 1 foot, 1 foot, 1 foot. You'd have 1 foot all around on this cube. And cubes, of course, have 6 sides. So the way you do an idea of how fast it takes to cool is the larger your surface, the more space you have for stuff to radiate out, the larger your volume, the more stuff you might have inside there. So one of the things that we see is we can divide out our area, which is always a square, and our volume, which is always a cube, which is 3-dimensional. So that gets rid of 2 out of 3 r's, just 1 left in the bottom. And since we're dealing with spheres and circles here, we have our pi in there. Don't worry about y. And we don't really need to geometrically worry about why 4 is here, but these cancel out with each other and you just have this. So that tells you if we have a larger r here, we're going to cool down more slowly. If we have a smaller r, we're going to cool off more quickly along the way. So the larger you are, the more likely you are to have heat inside. And if you have heat inside, you are likely to also have a magnetic field being generated from the stuff inside, because we get magnetic fields by charging particles that are moving around, especially metallic particles. You can get magnetic fields from things that are not. The sun does a pretty good job making hydrogen into stuff that can be magnetic. We're nowhere close to being that powerful. But we've got iron and nickel and other kinds of stuff down there sloshing around really fast. We go around in 23 hours and 56 minutes. That's actually the operative number when we're dealing with this kind of stuff here. So when we deal with this, we are in fact generating a magnet. We live on a big electromagnet. To get a magnet, you need to have a molten interior that will conduct electricity. Hey, metal, hey, that will do. We need to have our convection bubbles, and we need to have a moderately rapid rotation. Guess what? Venus has not a moderately rapid rotation. We're going around in 23 hours and 56 minutes. Mars is going around just about 45 minutes longer than that. But Venus takes 245 days, not hours, days to go around. So it's just sort of hanging out there. Remember, it's also the one that's upside down, but it's not moving very fast. So it doesn't have the sloshiness the way the Earth has. It has some, but it doesn't have quite the field that we have along the way. So that's what's happening inside. There's a lot more to this, but you can read a little bit more on your own. And trust me, there are people who get entire degrees just in this stuff. What's happening on the surface? What happens below influences what happens on the surface, because what happens below can dictate whether we have volcanism and tectonics. Whether or not it's larger or smaller tells us whether we have an atmosphere, which contributes to erosion. no atmosphere, no erosion, and they all suffer from impact cratering. They all are susceptible to meteorite hits, asteroids, and comets. So we'll see how that happens. Since all of them are impacted at some point or another, we can see impact craters on all of the interior planets, including the moon as well. Craters are often about 10 times wider than the thing that made them. And small craters greatly outnumber the larger ones. And we can actually see a pattern happening. Remember that era of heavy bombardment when we had lots and lots of big things hitting? Well, over time, those big craters get covered with smaller craters, which get covered with yet smaller craters. We know the smaller craters came later because if the big crater came afterwards, it would obliterate all of those. So we can actually tell the timing of the cratering as it's happening along the way. We have some on Earth, Meteor Crater in Arizona. If you ever go to the Grand Canyon, this is worth a stop. Probably about the size of IU. You see the visitor center over here on the corner over here. This has lasted for 50,000 years, largely because in this part of the world, there's not a lot of rain, not a lot of snow, not a lot of erosion happening along the way. On the moon also, not a lot of erosion happening. So what we get in addition to the crater is a central peak, which is when there's an impact, it has a kind of explosion and it scoops up stuff in the center. And that stuff is very, very fragile. On Earth, it blows away very fast. No blowing on the moon because there's no atmosphere on the moon. So it tends to last. It still will be withered away over time from the solar wind, which are actually solar particles sandpapering it, but that can take thousands to hundreds of thousands to millions of years. We also have impact craters on Mars that we see. We can see this is eroded. We see this one is fairly pristine. We can see this one ended up on a frozen plateau. So that happens as well here on Earth. Then we have volcanic activity. So sort of live long and prosper, volcanism. Volcanic activity happens when magma, which is below the surface, reaches the surface and comes up and does something. We call it lava when it reaches the surface. Not really a lot of difference between magma and lava, except that magma is below the surface, lava is when it reaches the surface. Of course, when it reaches the surface, it starts taking on various atmospheric contaminants and other kinds of things like that. So it then changes. But effectively, for our purposes, magma below the surface, lava above the surface along the way. Three main types of volcanoes. We have all three on Earth and we have all three on Mars. We have a predominance of a certain type on the moon, and we suspect but haven't seen any volcanoes on Venus, largely because 100% cloud cover 100% of the time. But the largest volcanoes, when we sort of see a cartoon that Roadrunner and Bugs Bunny and others are running away from a volcano erupting, it's usually the stratovolcano. It's where the whoosh kind of lava just goes straight up and it has a smoke plume that goes into the stratosphere. So it sort of looks like almost a nuclear explosion. That's why it's a stratovolcano. Often also, the mountains that are built up from these can reach up into the lower level of the stratosphere. So that's one of the things that happens. We have several of those here on Earth. Then we have shield volcanoes. The best known shield volcanoes actually on Earth are probably the Hawaiian Islands, where you have the magma bubble up and then flow over and then flow over and then flow over, and it builds up, 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 and slowly builds up this mountain. One of the largest mountains on Earth is actually the Big Island of Hawaii, but most of that mountain is actually underwater. And it took a while for it to reach. We'll talk about that as a hot spot coming up. The biggest shield volcano is actually Olympus Mons, Mount Olympus, which is on Mars. It's the size of the state of Missouri. Then we have lava plains. We have a sort of lava plain kind of volcano right below the state of Wyoming. That's sort of what gives the geysers, like Old Faithful, their heat source along the way. But we look and see up on the sort of the Sea of Tranquility on the moon and the Sea of Storms and other kinds of things like that that are there, those are actually lava plains that from the earth at certain times look blue, so ancients thought they were seas, or maria. Mare is the Latin word for sea, and that thus they are called Maria, not Maria, on the moon. One of the things that happens is that oxygen and other things get leached into our soil. That's, as I mentioned before, oxygen is one of the main components of the subsurface of the earth, not just the atmosphere. But one of the things we see is that that gets returned, it gets recycled back into our atmosphere in different ways. And part of it is through volcanic eruptions. You shut off the volcanoes and you shut off that oxygen being replenished into the atmosphere. You shut off the geysers and volcanic vents and other kinds of things, and that takes a toll on the atmosphere. Guess what happened to Mars over here? What color is rust? Red. What color is Mars? Red. What happened to the volcanoes? They shut off. Where did the oxygen go in Mars? I'll bet it's in the soil. I'll bet it's leached into the material of Mars, and the mechanism for putting it back into the atmosphere has shut off. So actually volcanoes and other things like that, as destructive as they are pretty necessary for the life cycle of our planet. Then we also have tectonic forces. We've seen them on other planets in addition to Earth, but we're most familiar with them here on Earth. The plates move around and sometimes they squish against each other. And when that happens, we get mountain ranges and sort of folds. Sometimes they pull apart and we get big, deep trenches. Right now, there's a huge sort of gush between the Eastern Hemisphere, as we're talking Europe and Africa, and the Western Hemisphere of North and South America, because they're pulling apart from each other. The Appalachian Mountains here were formed largely when the North American continent and the African continent were right next to each other and pushing against each other, and it was buckling up the North American continent. That's where the Appalachian Mountains come from along the way. Pretty neat. Here we can sort of see all the way along the Atlantic. We have what's called the Mid-Atlantic Ridge. These plates here, Europe and Africa, are going towards Asia over here. These, the Americas plates, are going towards the Pacific here. So this is from almost from the South Pole, the Southern Ocean, all the way up to the Arctic Ocean, and it's all underwater all the way except for this place here. This is Iceland. This is the one place in the Atlantic where that ridge, where the plates are separating out, is above water. And you can go to various places where you can actually see the plates pulling apart. And you can stand in the center and say, that's Europe over there, and that's North America over there. And you can put 1 foot in one continent and 1 foot in the other continent. They've even filmed portions of Game of Thrones at one of those vents that's there. So it's pretty neat. Every time I go, I find some new place along the trenches that I haven't been to before, because it is a fascinating thing. And they change over time. Over my 40 years or more of going to Iceland, they have separated out more than I can put my feet in where I originally did 40 years ago. Erosion happens. We're used to that here in Indiana. Say if I take my my muddy boots and go out to the garden and sort of stomp around as I'm trying to pull up weeds, within a couple of weeks at most of those muddy boot prints that I made are going to be gone because rain, because wind, because growth, all sorts of stuff. There are all sorts of things that erode on our planet. Water is a key one. Of course, there's no water on the moon. There's no water on Mercury. There's no water anymore on Mars. So these things have shut off on the other planets. Way too hot for water on Venus. But this is a carved crevice. The Grand Canyon is more than 1 million years, actually millions and millions of years, if we're going to be correct, more than 1 mile deep here. And we can see the strata of the geological processes that built up prior to this cutting down and cutting through. Then we have glaciers. This whole thing used to be encrusted with ice. and the ice and snow would crack things apart. And this whole valley was created by glaciers. Here in Indiana, in the last ice age, the ice ages stopped, the glacier advances stopped just north of Bloomington in Martinsville. In Martinsville, they have their team name, the Artesians. That's a certain type of well water. Many geologists believe that that's a leftover from when the glaciers melted and receded. You'll notice that if you're driving south of Bloomington in Indiana, things get very hilly. If you go north of Bloomington, and especially north of Martinsville, all the way up to Chicago, what happens? It's very flat. You can have windmills and all sorts of stuff like that, that are out there, those big turbines. So I always know I'm getting close to the airport, or I'm within a couple of hours of the airport in Chicago, because I see the big wind turbines that are going up there. Can't do that in hilly and daily kinds of places so well. But when you've got lots and lots of flat land created by glaciers that have receded, you can do that. And that's one of the things. The glaciers from the old ice age are still with us, by the way. You know where they are? The Great Lakes. That's why the Great Lakes are fresh water and not seawater. They're not ocean water. That water is not from the Atlantic. That's all melted ice and snow. And that's why it's fresh water. They're still with us here. Then we have erosion by wind. There is erosion by wind on Venus. There is erosion by wind on Mars, although on Mars it's much less, it's much more gentle. There's no erosion by wind on Mercury or on the moon. When we say solar wind, that's not atmospheric wind. That's actually particles coming off the sun. That's something different. But wind will wear things away. We get our sand dunes. But if you're blowing wind, which will have tiny particles in it for billions of years against something like Mount Everest, it's going to wear Mount Everest away. Then we have erosion debris, stuff that floats down the river and creates this various almost paradise kind of area, because this is very fertile stuff. Lots of people, hundreds of millions of people on our planet live in these river delta areas. Half of the state of Louisiana is a river delta from stuff that's floated down the Mississippi, the Missouri, the Ohio, and other rivers that snake into that along the way. The entire country of Bangladesh, almost all of the people who live in Egypt either live along the river or in the Nile Delta. And we know that from way back in biblical times. That's where everyone lived, because that's where it's fertile. This happens over and over and over again all around the world. Again, you have to have flowing water on the surface for this, so we're the only ones with this. Impact craters help us to determine the age of a surface. Most cratering happened during that era of heavy bombardment and shortly thereafter, because as we're scooping up the material, there's not new material being generated, so we're running out. So a surface with lots of craters is probably about 3 billion years old or more. The moon and Mercury are mostly that old. Although we do have some areas which had our lava fields, these darker areas that you see here. Those are our mare, our maria. So when we're looking at those, that stuff that's come along later, we can see this. This is the whole moon. You know, if you take the globe of the Earth and spread it out into a flat map, you have all the continents. If you take a globe of the moon and spread it out, this is what it looks like. And this is pretty much in the middle here, the surface that faces us. The more cratered stuff faces away from us along the way. But this stuff tends to be newer. So it is also the area that smoothed out older craters, because the lava flow would smooth things out. How would it smooth them out? Well, it would smooth them out because it would weaken the surface and almost act like an iron from underneath to make it more smooth along the way. Different planets have different histories, largely because of planet size. We talked about how smaller bodies cool off faster, the larger bodies keep their heat, and the dynamic things that are happening inside. Distance from the sun also makes a difference, because if you're Mercury, especially if you don't have an atmosphere, too hot for rain and snow and ice and other kinds of things that are there. Also too cold on the other side for anything liquid. The face of Mercury away from the sun is one of the coldest spots in the solar system. So when we're further away from the sun, we're in the Goldilocks zone. For us, we can in fact have just right. So how the distance plays out makes a difference. Also rotation. Slower rotation means less weather and less erosion and a weaker magnetic field. Hello, Venus. Although Venus does have some really fast winds, especially in the top of its atmosphere along the way. Faster rotation gives you more weather, more erosion, and more magnetism. So our moon, as we've talked about before, we have our smooth areas here. You can see this, we've had a big impact crater here. Notice one of the things that's happening here in this impact crater. We have these jets of material. That's called ejecta. So these are ejecta blankets. So you have an impact and it spews things out in the different directions. The brighter the rays, the newer the impact because they fade over time. The darker stuff is where we've had the lava flows, usually from underneath that's happening. And what we can see here in this demonstration, we had a lot of impact 4 billion years ago, era of heavy bombardment and such, boom, 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 just knocking everything out in the moon. But as it would knock a really big impact, it would weaken it down to the layer where the lava is flowing underneath, and it would, as I mentioned, act like an iron underneath and smooth it all out. We know that the heavy bombardment stopped because if it hadn't stopped, this would have been filled in with more craters along the way. So it helps us age things. We can also see over the course of time with the cooling that things tend to contract. Now, this may seem counterintuitive to you because how many of you have ever put a can or a bottle of something in the freezer and had it explode? Well, water is the one thing, the one main thing that acts differently from other things. Most things, when they cool off, contract. You may notice this in like your doors and your windows and other things of your house, or things that are outside in the wintertime. Things will contract in the cold and they expand in the heat. Water is the one key difference, but there's no water on the moon. So as the lava is cooling, it contracts and then we get wrinkles that occur from that. So we mentioned that there's no erosion except for a very, very fine kind of solar wind. We don't have volcanic activity anymore. We don't have tectonic plates on the moon that are shifting around. So things on the surface tend to stay on the surface until they are impacted by something from outside. So if an impact crater, if a meteorite comes and hits this, it'll obliterate the boot print. We also have the sort of sandpaper effect of the solar wind. So that will eventually wear it away in hundreds of thousands or millions of years, but that same boot print in my garden is gone within a couple of weeks. That's one of the differences. We see the same kinds of stuff happening on Mercury. Here we can sort of see smoother areas. We can see some impact craters with their central peak. Remember when we have the explosion that pulls material up, that's the central peak. Mercury has a mixture of surface features just like the moon does, so it looks very similar to the moon. We haven't had many missions to Mercury, but we've been up close and personal with it a couple of times, and we have a mission on the way there right now. But it's not nearly as interesting as Venus or Mars because it doesn't have an atmosphere and it doesn't have a lot of things that we can't see more or less on the moon as well, and the moon's a lot closer. But there are a couple of differences that make it worth sending a probe maybe once every 15 to 20 years. So that's what's happening right now along the way. One of the things we do have is that we have some hollowed out areas where there's gas escaping because on Mercury, on the sun side, it heats up 420 degrees Celsius or so. And on the cooler side, it cools way down to minus 150, minus 170 degrees Celsius. So it goes from hot to cold to hot to cold along the way. And one of the interesting impacts on Mercury is it hit so hard on Mercury that it actually cracked the other side. And we can tell from the cracks and fissures on the other side that they're related to that impact that happened. We also have these crevices that are like this. We actually call them scarps. This kind of cliff here could be as much as half a mile drop from one point to the other. And we can see that this happened after these craters occurred, because if the crater came along afterwards, it would have obliterated the scarp. And this is part of that contraction, part of that wrinkling thing as the planet cools off. And sort of you can see here, as the planet itself cools off and contracts, we get these crustal movements, which again are called scarps. Then we have Mars. Now, once upon a time, we have a guy named Percival Lowell who had what was for a brief time the best telescope in the world. And he looked at Mars and he thought he saw this. This is what we see when we look at Mars with that same telescope and that same kind of power. Where are all these lines coming from? Well, there's one enterprising ophthalmologist who speculated, put forward the theory that, and if you've ever looked in a telescope, you may notice this, especially a reflecting kind of telescope, but this can happen with other telescopes as well. When you look inside, you sort of have to look around, because it's not just sort of look and see. You have to sort of find the image inside there. Well, if you're looking inside, you might actually get a reflection of your own eyeball back. Some people notice that and if you go to a doctor's office, an optometrist, an ophthalmologist's office, they have devices that will let you see, or let them see, the back of your eyeball. They'll sort of aim the light through and you'll see the retina. Well, guess what? This might be the retinal pattern of Percival Lowell. He might have actually seen this, but he saw that on top of the image of Mars. What color is Mars? Reddish. What color is your retina? Reddish. You wouldn't have noticed from a color variation. So it's sort of weird. This is where we get the canals on Mars. Now, there was an astronomer, an Italian astronomer named Schiaparelli. And Schiaparelli, before Percival Lowell was doing all this, wrote about canali on Mars. Now, canali in Italian should be translated more like channel. When you hear canals, you typically hear, oh, those are made by human beings. Panama Canal, Suez Canal. I got me a mule and her name is Sal, 15 miles on the Erie Canal. Yeah, I won't sing it for you. Trust me, you don't want to go there. But if you hear channel, you might hear, oh, English Channel. That's a natural formation. Well, Percival Lowell heard canals, not channels. And he was convinced that little green men, LGMs, were making up these canals along the way. And this inspired people like H.G. Wells, War of the Worlds, Orson Welles with the radio broadcast and movies, all the way up to today, War of the Worlds. Mars, never quite as interesting as this in terms of canals, but it is really interesting in other ways. And we've landed there again and again and again. We started landing there in the 1970s. Viking 1 and Viking 2 were sort of the premier Let's Land on Mars program for the bicentennial of the United States. Viking 1 here, Viking 2 there. They are just landers. They sort of land there and do experiments and pictures around. Then later we got a little bit more adventurous and went up to the North Pole and went to different parts. And then we started putting different Spirit, Curiosity, Opportunity rovers, Pathfinder rovers that could move around. At first just a little bit, and then more and more and more and more. Pathfinder was about the size of a toaster oven. Spirit and Opportunity were about the size of a dune buggy. Curiosity is about the size of a Jeep. So yeah, we are getting bigger and bigger as we do these different things so that we can learn more about the surface. Notice on the surface, not a lot of canals. We've got this one big long thing here. Maybe that would have been one of the things that Schiaparelli thought he saw. We're not too sure he saw it either, because with the magnification power and resolution power of what he was using, typically Valles Marineris is not visible. So we're not quite entirely sure there either. But we can see we've got volcanoes, we've got smooth areas, we've got really pockmarked areas, but we've got some smooth areas inside the pockmarked areas. We've got polar ice caps. We've got some really interesting stuff happening here. The cratering is different. Smooth areas up here, craters down here. Many early craters have been erased. What did it? Oh my goodness, hey, there's one of our first clues for water on Mars. Once upon a time, most of this area up here was probably an ocean or two on Mars. We have volcanic activity on Mars. Again, here's Olympus Mons, largest volcano in the solar system. This whole area is the size of Missouri. If it were a state in the next election, it would have 3 electoral votes. So yeah, and what party would it be voting for? It's a red planet, red state. Bad joke, I know. Never mind, bad jokes are free. We know that this volcano has shut off a long time ago because look here and here and here. We've got craters. Those would have been smoothed over by lava if lava was still flowing. So the lava hasn't flowed here for a long, long time. You may remember a movie called Total Recall with Arnold Schwarzenegger, and he goes inside and turns on a device inside this big mountain. You see him like going in a door down here and running to the center. This is the size of Missouri. It takes me 5 hours to drive from St. Louis to the center, and I'm going at 80 miles an hour. Well, I'm going 90 miles an hour, but he's not running 90 miles an hour, and he can't get there in the time that it would take him to not die of asphyxiation. So yeah, that's a bad movie scientifically. Good movie in other regards. But yeah, I sit there and nitpick at the science and say, you know, they just had to show me the script and I would have told them for free. But never mind. This is the biggest shield volcano there is. There are several others, though, you may notice here, here, and here, along with Olympus Mons. This looks like it's in one of the watery areas. So these may have actually been island tops, the way the Hawaiian Islands are along the way. Then we have Valles Marineris. This may have been a lava tube because it seems to be flowing up towards over here is Olympus Mons, just off of this. But this whole thing is as long as the continental United States. And it's very deep as well. So we're talking 10, 20, maybe even 30 miles deep in certain portions of it along the way. So this is not the Grand Canyon. This is something much more significant. But we do have interesting things like this. This is one of those sort of trick kinds of puzzles. If you sort of look at it, it looks like it's bubbled up. But then when you look at the right way, you see it's actually angled down. This is, in fact, a riverbed, most likely. We have lots of dried up riverbeds on Mars. We have areas where we can actually connect the oceans via these riverbeds to smoother areas. Again, if a meteorite hits in this area, it's not going to leave a crater. And then we have these other areas that we can see look like they have been washed away, or we've had the river delta deposits. Again, just like Louisiana, just like the Nile Delta in Egypt. We have rivers that are flowing through and depositing the debris as they are flowing down. Then we also have this. I love this comparison because what a lot of people don't know, when you're visiting Arizona or New Mexico or Utah or Nevada, you're actually standing on the bottom of an ocean. That used to be a giant inland ocean. Most of it's dried up. There's a little part of it left. It's called the Great Salt Lake. Notice that lake is salty because it used to be an ocean that dried up. The Great Lakes are not salty because they are melted glaciers. But there's something that happens at the bottom of salty kinds of oceans like this. We get these things. They're called blueberries. They're not blueberries that you put in yogurt and eat. They're actually small metallic balls that are made. But we pretty much only ever see them underwater or places that used to be underwater. Look over here at Mars. they're all over the place in certain areas. Looks like there might have been water here. And then when we look at the way that the cracking that's happening here, it looks like that might have been underwater as well. We look at rock formation areas. We find different things that look like they were clumped together in stream beds. This kind of clumping happens underwater. And then this kind of stratification and sediment deposit happens as the shoreline is being lapped by the ocean. This is what happens. You get the sandy area where the water is lapping up against it along the way. Lots of indications of lots of water that used to be there on Mars. And every now and then we get these things. Look at these streaks. There's water just below the surface that's breaking through. As soon as it breaks through, it evaporates or freezes. So it doesn't last long. There's not enough atmospheric pressure on Mars to keep water liquid on the surface anymore. It's not just a matter of temperature. You've got to have enough atmosphere pressing down to hold it into a liquid state. We have that on Earth. We don't have that on Mars anymore, but we may have once upon a time. As we send our rovers around, they drill, they use microscopes, they use various other kinds of things, including blasting rock with lasers to see what comes out of it, what kind of debris, what kind of other stuff happens. And we're getting really good at this. Next up on Mars, sometime in the next 15 to 20 years, we'll probably have drones that are able to fly around as well. But one of the things for drones, you have to have an atmosphere. We can have drones here because we've got an atmosphere. If you've only got 1% of the atmosphere that we have here on Mars, that's going to be hard to lift up things. So we're experimenting. We're still developing things. On the other hand, if you want atmosphere, you go to Venus. Venus has nothing but atmosphere. Well, it's got a lot more than that. But if you think about Earth as one, then we're looking over here at Venus. It's 100 times the atmosphere. If you're thinking of the Earth as one, then Mars over here is 1/100th. So Earth is 1, Venus is 100, and Mars is 0.01. So if we're thinking Mars as 1, we can have the Earth as 100 and Venus as 10,000. There are 10,000 times the pressure and atmosphere on Venus as there is on Mars. But that creates a weather kind of situation with the clouds where we can never see below the clouds unless we get tricky. We can radar map. The entire surface has been radar mapped, but we've never actually seen the surface from above the clouds because the thick atmosphere never dissipates. But we have seen with this craters. We see the concentric rings from where there was an impact where it sort of threw things out. Fewer impacts than the moon or Mercury or even Mars because the atmosphere erodes things. We also have other kinds of volcanic activity. We've not seen the activity in terms of an actual eruption, but we have seen different kinds of shield volcanoes and different kinds of stratovolcanoes. These are sometimes called pancake volcanoes here. They're stratovolcanoes that sort of blob up into these kinds of things that are here. We also see tectonic forces. We see sort of plates moving, but plates on Venus are much, much, much smaller. We've got like the North America plate and the South America plate and the Africa plate and other things on Earth. On Venus, they're platelets, and there are tens of thousands, maybe hundreds of thousands of them, more like county size things that are moving around. We have actually landed on Venus. Now, Venus is 470 degrees Celsius day and night, which means we're talking it can melt lead, it can melt iron. So here's the thing. When we send Spirit, when we send Opportunity, when we send Curiosity to Mars, we plan for them to last 60, 90, maybe 180 days. And they end up lasting 7 years, 13 years, however many years. Years and years and years and years. When we land on Venus, the record for landing on Venus is about 2 hours. Not 2 years, not 2 months, not 2 days, 2 hours, and the average is less than an hour before everything melts and goes kaput. So yeah, we have pictures of the surface. We don't have any rovers on the surface. We're not sending any drones there anytime soon, and we're certainly not moving there anytime soon. So it has plate tectonics with the little platelets, but it doesn't have the big kinds of plate tectonics. So we don't want to really call it plate tectonics there. So if you have a true false question, I would say no to plate tectonics, but it's got tectonic-like kinds of things. So we're not entirely sure why that is. Is it because it has weaker convection bubbles because it isn't spinning as fast? Or does it have a thicker lithosphere? Has it actually cooled off a little more, despite the fact of how hot it is? Has it actually, in fact, cooled off more from the center than we have? So our planet, again, big plates that are moving around here. We can actually measure this with GPS. GPS has to be updated on an ongoing basis every day to take into account the shifting of the plates that are taking place. We can see, almost like jigsaw puzzles, where different things have fit together. Again, if you look at this portion of South America, this portion of Africa, they look like they fit together. This portion of Madagascar looks like it fit there because once upon a time it did. Here's a weird thing. This portion of North America, from Florida to Maine, fit right over here against Africa. And in fact, to this day, the closest part of the United States to Africa is Maine, up north, not Florida, down south, because of the curvature of the Earth, and the plates used to be against each other here. This portion of Asia here, which is called the India subcontinent, used to be attached to Antarctica down here. This portion of South America used to be attached to this portion of Antarctica once upon a time. We've been shifting around, and as we shift around, it spreads things out. The continental crust tends to be older and denser, but the seafloor tends to be younger, newer, and less thick. It's one of the reasons why people will drill out in the sea, because you're drilling through a lot less. It's easier to drill through water than it is through rock. And as you're out there, even with the dangers of being out there, it's actually a lot more economical in a lot of ways to drill offshore. Seafloor recycling takes place in two different ways. When one plate goes under the other, we call that subduction. This Pacific plate is going under North America. That's what's building up the mountains in the western half of the United States. Then when we have this sort of separation here, we have an eruption of new seafloor that happens in the mid-Atlantic as things are happening there. So we have a lot of features that are related to that. The Appalachian Mountains, as I mentioned before, happened when this portion of the United States, or this portion of North America, was bumping up against the continent of Africa, and it was crumpling it. Look how dense and high these mountains are over here. That's because this plate is being pushed up as the Pacific plate is being pushed down. And they're not just going directly towards each other, they're actually sliding against each other as it happens. And that's why we get earthquakes so frequently and volcanoes so frequently all along the West Coast. Here we can see the India plate being pushed up under, subducting under the Asia plate. So as it goes under the Asia plate gets pushed up. Here are the highest mountains in the world, the Himalayas. Notice they're all snow-capped peaks. They're all like 5 miles up in the sky. This portion down here is being pushed under, and as it does it, it pushes it further and further and further up. This is a collision of plates. Here we can see two plates that are sort of separating out. The Arabian Peninsula and Africa are actually shifting away from each other. So the Red Sea is in fact separating out, getting wider. We have volcanic activity in the Sinai. You may have heard of Mount Sinai from biblical stuff and how there were rumblings and stuff happening there. Well, that's a pretty good indication of a volcano. You may have heard of cities called Sodom and Gomorrah. Oh my goodness, they were killed off by fire and brimstone. That sort of sounds like a volcanic eruption as well. There was a story about people walking across on dry land, the sea bottom here. Guess what happens when there's an earthquake out at sea? it will often pull the water away and you can walk across on dry land. And then, of course, it says Pharaoh's chariots come along. And what happens when the water rebounds? Tsunami. Yeah. I'm not saying that that's exactly what happened, but I am saying this. I will say this. The stories that we have in the Bible and the stories we have in Egyptian religion and other religious texts of that area are actually pretty good at reflecting some of the ideas of the environment they lived in. They lived in an earthquake zone. They lived in a volcano zone. They lived in a place where the ground can shake and the walls can come tumbling down. That was the nature of this place because the plates are moving. When we look at the San Andreas Fault, we can sort of see the big shifts happening here. We can see where major earthquakes have happened as the plates are rubbing up against each other and one's going under. The Pacific Ocean plate is going under the North American plate that's over here along the way. But as the plate of the Pacific moves around, there's this hot spot sort of in the middle. What's happening there is lava is bubbling up. And as it bubbles up, it creates a mountain. And then the plate moves and it creates another mountain, and the plate moves and it creates another mountain, that moves and creates another mountain. So it's sort of like one of those, if you've ever seen a cake made on an assembly line, and what it does is it has a little icing maker, and the little icing maker comes down and it makes a little plume, and then the cake turns and it makes another plume, and the cake turns and it makes another plume until you've got the plumes all the way around. That's what's happening here. Only the cake maker plume is coming from underneath, and that's lava. We have all of the Hawaiian Islands formed as the plate moved and slowed down. That's why that last island, the big island of Hawaii, is so big. The plate slowed down and it's just stopped there for a while. But when it was really going, we have this mountain range chain that's taken place over the course of like 40 to 50 million years, 1,000 miles long or longer, all the way from Hawaii up to Midway Island, and then even beyond that, up into this area. We had no idea these were here until we got into big ships and submarines. And it's like, oh, hey, there's a whole long mountain range. These are failed islands. The hot spot didn't stay there long enough for it to bubble up to the surface. But if we were to take away the ocean, we'd see this mountain range all the way through. The Hawaiian Islands and Midway Island are, in fact, the tops of mountains that were created this way. And the hot spots already moved off of the great island of Hawaii, and the newest Hawaiian island is already being formed, Loihi. It's already named Loihi. So if you want to get your condo reservations now, in about 1 million years or so, it should be ready for you. As we look at the way the plates move around, we can see 200 million years ago, all these things together. Here's North America, South America up against Africa. We can see they begin to separate out to where we are. Notice what's going to happen 150 million years from now. Antarctica is reaching up towards Australia and towards Asia. We're going to lose the Red Sea entirely. We're going to lose the Mediterranean entirely. And North America and South America are going to be a little bit closer together, but South Africa is going to be close to the equator rather than down below. Things are continually shifting and continually moving along the way. So if you want to look for something, I'm going to try to, and in fact, I'm going to write myself a note so I don't forget here. I am going to post up a video on a place called Pangaea. And Pangaea is the name of the last great supercontinent. Pangaea, if I can get my little typing thing here. Pan as in everything, and Gea as in geology, geological, geo, that means Earth. So Pangaea, the whole Earth, is essentially one continent. This has happened again and again and again and again and again. We've moved around quite a bit in these things, but I'm going to post up a video from one of the other services. I think probably National Geographic may have something on it, or the History Channel may have something on it, so that you can see that. Now, when we look at planets, If you're too small, you don't have enough gravity to hold onto an atmosphere, and you cool off really quickly. So your magnetic field would also not hold onto an atmosphere. So you're not going to develop what we have in the Earth. Mars is the real question mark because it's smaller, so it didn't have enough gravity to hold onto the atmosphere for very long. But as long as it had a magnetic field, as long as there was stuff sloshing around inside, it might have been able to hold on with a magnetic field, keep the solar wind away, and it might have been able to hold onto an atmosphere long enough to keep a liquid ocean for a while. And that seems to be what we're seeing. But as it cooled off, the magnetic field left, the solar wind acting like a little sandpaper. Doesn't have to be much. Over billions of years it adds up. It's leached most of the atmosphere away. And of course, the water evaporated and dissipated. And the oxygen in the atmosphere that was still left got leached into the soil, but the volcanoes had shut down and nothing was being put back in. So are we destined to look like this based on how big we are and where we are in space? Some people say pretty much yes. We are determined by our size, rotation, and distance from the sun. Plate tectonics, well, and it's anyone's guess just how important any one feature is, but all of the features together make us what we are along the way. And I think this is one of those sort of interesting things here. Now, I want to find something because this presentation was in fact rather interesting, but there is a picture somewhere that I want to see if I can find. Okay, well, I paused it there for a moment, so hopefully you didn't see the whole long pause. I want to show you one more picture that I've used in previous lectures that's really astounding to me with regard to erosion on Earth. And let me see if I can share the screen here. It is this picture right here. And let me see if I can get to this one here. Look at that. This is the result of glacier erosion, of ice erosion. It split the mountain in two. What happens is, again, as I mentioned before, most things when they freeze contract. Water expands. And water, when it expands as ice, is hard as rock or even harder, which is one of the reasons why our roads erode, especially here in Indiana, as often as they do. You just have to get a little bit of water inside there to freeze and break apart the rock. That's what happened here. I mean, look at this stunning, stunning thing that happens here. So ice and water, ice baby. Yeah, I wanted to share that picture with you because it didn't show up in the other slideshow, and I thought, we're missing out here. Again, I know this took a long time, and I thank you for bearing with me. And I hope that last picture was a good treat for you in doing so. And I will look forward to seeing you in chapter 10.